So in the last video, we talked about bonds between molecules, in particular the hydrogen bond. So in this video, we'll be discussing not only the hydrogen bond, we'll be discussing the dipole-dipole and van der Waals forces. Those three are all between molecules. So the first and the strongest bond between molecules is obviously the hydrogen bond. And remember, the hydrogen bond is between strong dipoles. So it's like these three are super strong dipoles. Those three, water, ammonia, and hydrogen fluoride. Now don't forget, it's between the molecules. So if these two are water molecules, stick figures, so what would happen is water is sticky, like we said on the last video, so they stick together because they have a strong negative end, which is the oxygen, and a strong positive end, which is the hydrogen. All right, so now what I'm doing is I am putting electrons from the fur onto the balloon. So the balloon is going to be very negatively charged. And what we know is when I open up this, the water's going to come out and it's going to tumble. But this is negatively charged, and we want to show that water has charges. So when the water detects this negatively charged balloon, watch what happens. So here we go. So we're going to turn this on, going down nice and easy. And that is what's happening with the water. So what exactly happened? As the water cascaded down, the positive hydrogens were attracted to the negative oxygen balloon, and it went like this, then all of a sudden, boom, it came like this. So once again, the positive hydrogens from the dipole water were attracted to the negatively charged balloon. So it would cascade down, and then all of a sudden the positive hydrogens would be attracted, and then it would drop down like that. That's why the water missed the cup. Okay? So water definitely has a strong positive end and a strong negative end. It's a strong dipole. So as we saw in that demo, as the water comes down, normally we have a negatively charged balloon right there. So the hydrogens get attracted, and it looks like this. They don't go straight down. They're going to start going like this. And then like this. And then down. So they go right around the negatively charged particle, and they don't go straight down anymore. They come at a curve, all right? That definitely shows that water molecules have a positive end and a negative end are extremely polar. Very strong dipoles, which can attract other strong dipoles, and once again, strong dipole H2O attracting other strong water molecules hooked together by a hydrogen bond. Okay, so if two water molecules came close together, they'd kind of look like that, where the O from this molecule is hooked to the H from that molecule. And the hydrogen bond would be between the two molecules. All right, that's a hydrogen bond. And those are the things that have it. Now, remember the properties. High boiling point, because you got to break all those bonds in order for it to vaporize. High boiling point and low vapor pressure. They don't want to evaporate because it takes a while. And don't forget, water is sticky. That's why it's spherical. All right, they all want to stick together. That's the first one. The second is the next weakest. Remember, that's the strongest bond between molecules of hydrogen. Then we have this one. dipole-dipole attraction. And that's between like normal polar molecules. So let's say this one. HBr and HBr. So remember, Br is not as electronegative as water, as O, N, or F. So it's a teeny positive, teeny negative, teeny positive, teeny negative. And there's an itty bitty little thing like that. So that's dipole-dipole attraction, but it doesn't give, if that was a liquid, it wouldn't give it high boiling point and low vapor pressure. Dipole-dipole attraction is fairly weak. So hydrogen bonding is the strongest between the molecules. Then we have dipole-dipole attraction. And now the one that we're mainly going to talk about today is van der Waals forces. And that's number 3. The other name for van der Waals forces would be London dispersion forces. That's the third one. This is the weakest force between molecules. But what kind of molecules? Remember, hydrogen bonding is between strong polar molecules or dipoles. Dipole-dipole attraction is between average or weak polar molecules. This, van der Waals forces, is between non-polar molecules. And you ask, how can non-polar molecules attract each other if they don't have any poles? Well, it's really the electrons in the nonpolar molecule migrate from one end to another end, one end to the other end, and they can attract that way. But we're not going to talk about that in high school chemistry. We're going to talk about how nonpolar molecules can attract each other, high school chemistry wise. So, I've drawn 2 propane molecules. Now look at them. Those propane molecules are symmetrical. Symmetrical molecules are nonpolar. They don't have any poles. How can these 2 attract? Well, they don't normally attract. So how can we make them attract? Well, 2 things have to come into play to make them attract. They have to be very close together, and it helps if you have a low temperature. So these 2 propane molecules are like this. They're gas molecules, all right? They're like this, and then if we freeze them, they stop moving, and then if we put tremendous pressure on them, they get closer, 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 closer together, and bang, they turn into a liquid. And you all know this because propane tanks, when they fill them, if you shake them, there's liquid in there. But when you open up the valve and release the pressure, the propane molecules blow right away. All right, the bond is so weak that if you release the pressure a little bit, they move a little bit further apart and they turn into a gas. Okay, so the 2 things that we could put nonpolar molecules together, we need high pressure and low temperature. All right, that's what could keep these molecules together. So we can take a gas like propane and turn it into a liquid. Now, the other cool one is this. Hydrogen gas, that's the lightest. Now, the very cool thing about hydrogen gas is during the space shuttle days, what they had in the booster rockets was solid hydrogen. How in the world do you make solid hydrogen out of hydrogen gas, which is super light? What they did is they took those gas molecules and they really froze them and they put them under pressure, and that hydrogen gas turned into a liquid, but it was so cold that it actually turned into a solid. So, in order to turn hydrogen gas, these are nonpolar molecules. So once again, nonpolar molecules, the two things you have to have to make them attract: low temperature and high pressure, and then they can come together. But remember, it's a wickedly weak bond, so the minute the pressure is released or the minute the temperature goes up, boom, they are apart. All right, everybody understand that? So the deal with this bond is you need high pressure, you need low temperature. So let's talk about this. The properties of liquids or solids held together by van der Waals forces. Well, the first property is they don't want to stick together, so obviously they have a really low boiling point, and it wouldn't even be worth boiling because a lot of the nonpolar molecules come from petroleum and they're flammable. So, low boiling point. But the most interesting property is this one. They have a very high vapor pressure. And don't forget, what's vapor pressure? How fast the substance evaporates. So, I mean, take gasoline. So you're filling up the tank with gasoline and you spill a little bit on the cement. So you put the hose back, you go over, get a paper towel, you come back, and it's gone. All right? It evaporated that quickly because that liquid, octane, is symmetrical and it's only being held together by kind of pressure and lower temperature. So the minute one of those, the temperature goes up or the pressure goes down, it's gone. It's gone. Those molecules do not want to stick together. So remember, van der Waals forces, the molecules have to be really close. If they're not close, there's not going to be any van der Waals forces. Those are the two big properties: very low boiling point and high vapor pressure. We'll do a little experiment on that, because remember the experiment we did with the water droplets on a penny? They balled up into a sphere. This stuff doesn't want to stay together, so it may not ball up into a sphere like water. All right? So remember, in order to have van der Waals forces between nonpolar molecules, they have to be very close together. And the best group that shows van der Waals forces is this group. The halogens, all right? Fluorine gas, it's very light. The molecules are really pretty far apart. Gases cannot have van der Waals forces between them because the molecules are too far apart. Chlorine is a denser gas, but the molecules are still a little bit too far apart to have van der Waals forces between them. But bromine is a liquid at room temperature, so that means the molecules are closer, almost touching. So bromine does have a bit of van der Waals forces holding it together. But now, iodine is a solid. Those molecules or those atoms are right touching. They're right next to each other. So what I'm telling you is, going down a group, as the size of the atoms get larger and closer, you have more van der Waals forces. Going down any group, van der Waals forces increases with molecular weight. Okay, and remember, van der Waals forces is the weakest bond between nonpolar molecules. So what we have, hydrogen bonding between strong dipoles, that's the strongest between molecules. Dipole-dipole attraction, it's pretty weak between normal polar molecules. And then we have got the weakest, which is van der Waals forces between nonpolar molecules. And remember, nonpolar molecules, they don't want to stick together. They don't want to do that at all. Okay, so now we're going to do a couple little demos. Okay, so remember what I said before, as we go down a group, as the molecular size increases, van der Waals forces also increase. So fluorine light gas, no van der Waals forces. Chlorine denser gas, no van der Waals forces. But bromine, remember, it's a liquid, it's heavy, so it's got a little bit of van der Waals force. Iodine, really heavy, definitely a solid, van der Waals force is the strongest. So going down any group, VDF increases. But these, as the weight increases, so does van der Waals forces. CH4, very light methane gas, not very much van der Waals forces at all. But here, propane, heavier, but not very much van der Waals forces unless you put high pressure, low temperature. Octane, gasoline, getting heavier, definitely has van der Waals forces between the molecules. And finally, we get to something like motor oil, is much heavier than the other ones, and they have definite van der Waals forces between the molecules. Okay, so the heavier a substance gets, the more van der Waals forces it gets between the non-polar. Right, so this is a great little demo. This is water. Okay, now watch. I'm going to put 10 drops on this penny, and you're going to see the property of hydrogen bonding. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So look at it. It didn't even coat the penny. It's all like a sphere. And remember, water has hydrogen bonds, so it's pulling the outside water molecules into the center. That's why water forms droplets or spheres. Now the next one is lighter fluid. It's non-polar, and so that means it doesn't have hydrogen bonds between it. Watch what 10 drops does to this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at the difference between them. This is water held together by hydrogen bonds, and this is lighter fluid, and it's not held together whatsoever, so it flattens out. So now, hopefully, you really understand that hydrogen bonds have strong intermolecular forces. As you see on the left penny, they're all still together in a sphere, not even coating the penny yet. While van der Waals forces on the right with the lighter fluid, they don't have anything holding it together, just van der Waals forces, which is a weak intermolecular force. Also, the property of hydrogen bonds, that water, since it's stuck together by hydrogen bonds, has a very low vapor pressure. It's going to stay there for a while on the right side, the lighter fluid, that's going to be gone in several minutes or less than that because it has a very high vapor pressure.